Welcome to Methods in Biostatistics. Today, we are diving into one of the most fundamental concepts in all of science, the null and alternative hypotheses. Whether you are testing a new vaccine or studying animal behavior, this is how we separate true discoveries from random chance. Let us get started. To understand how we test scientific claims, imagine you are sitting in a courtroom. In the justice system, a defendant is always presumed innocent until proven guilty beyond a reasonable doubt. The baseline assumption, or the status quo, is innocence. The burden of proof lies entirely on the prosecutor making the new claim of guilt. In biostatistics, we use the exact same logic when testing a new scientific idea or medical treatment. We start by assuming that nothing special is happening. We only change our minds if the data provides overwhelming evidence against that boring baseline assumption. Now that we understand the courtroom analogy, let us translate that baseline assumption into the language of statistics. We call this the null hypothesis, which we write as H0. The word null literally means zero, empty, or nothing. This perfectly describes what this hypothesis claims. There is no effect, no difference, or no relationship between the things we are studying. It is the skeptical position. Just like we never truly prove a defendant is innocent, we never actually prove the null hypothesis is true. We simply check if we have enough evidence to reject it. Since the null hypothesis represents the boring status quo, what represents our actual scientific theory? That would be the alternative hypothesis, written as HA. This is the exciting new claim that the researcher is actually trying to prove. It represents the idea that there is a real effect, a significant difference, or a meaningful relationship present in the population. When we conduct a statistical test, we are mathematically pitting these two opposing statements against each other. We want to see if our data is strong enough to support this alternative claim. You might wonder why we have to go through this backward-seeming process of assuming nothing is happening first. This framework is the absolute backbone of the scientific method because it prevents researchers from making false claims based on random chance. For example, if a pharmaceutical company creates a new drug to lower cholesterol, they cannot just give it to 5 people, see a slight drop, and claim it works. That drop could just be a random coincidence. By forcing the company to start with a null hypothesis, we protect the public from useless or dangerous treatments. Before we look at the mathematical formulas, we need to understand what we are actually measuring. To test these ideas mathematically, we must translate our plain English sentences into formal statistical symbols. We do this by making claims about population parameters rather than just looking at our small sample of data. A parameter is simply a numerical summary of the entire population, like the true average or mean, which we represent with the Greek letter mu. By using parameters, we make it clear that we are trying to discover a universal truth about the whole population. Now that we know about population parameters, let us look at how we write our hypotheses mathematically. This formula setup is used when we compare a new treatment to a known historical baseline. The null hypothesis, H0, states that mu equals mu0. Here, mu is the true average of our new population, and mu0 is the historical baseline. The equal sign means we assume nothing has changed. The alternative hypothesis, HA, states that mu is not equal to mu0. This means we believe the new mean is significantly different from the baseline. If the true mean increases or decreases significantly, our data will push us to reject the null hypothesis. Let us see this formula in action with a practical example. Suppose the historical average recovery time for a specific viral fever is exactly 7 days when patients take a standard medication. Scientists develop a new experimental drug. What is given is the historical baseline of 7 days. We set our null hypothesis to state that mu equals 7, meaning the new drug has no special effect. Our alternative hypothesis states that mu is not equal to 7. The scientists run their trial and find the average recovery time drops to 3 days. Because 3 is so massively different from 7, this provides strong evidence to reject the null hypothesis. We can confidently conclude that the new drug truly works. Moving beyond a single historical baseline, what if we want to compare two distinct groups directly? This formula shows how we set up hypotheses for two unknown population means. We define the population mean for group A as mu A, and for group B as mu B. The null hypothesis states that mu A minus mu B equals 0. This is just a mathematical way of saying that both groups are exactly equal and neither is superior. The alternative hypothesis states that mu A minus mu B is not equal to 0, meaning there is a real measurable difference between the two groups. This setup allows us to compare treatments without needing a historical number. Let us apply this two-group formula to a real-world scenario. Imagine a nutritionist wants to know if diet A and diet B lead to different amounts of weight loss over a 6-month period. We are not given a historical baseline, so we compare them to each other. We set our null hypothesis to state that the difference between their averages is 0, meaning they are equally effective. The alternative hypothesis states the difference is not 0. The study results show that diet A causes 10 kilograms of weight loss, while diet B only causes 2 kilograms. This large gap of 8 kilograms provides undeniable evidence to reject the null hypothesis, allowing the nutritionist to confidently recommend the superior diet. To solidify everything we have learned, let us look at this visual representation of our hypotheses. On the left, you see a perfectly balanced scale representing the null hypothesis. The treatment and the placebo weigh exactly the same, illustrating that there is no difference or no effect. This is our boring baseline assumption. On the right, you see an unbalanced scale, representing the alternative hypothesis. The treatment side is heavier, showing a clear, measurable shift compared to the placebo. This illustrates a significant difference. Our goal in biostatistics is to collect enough heavy evidence to tip the scales away from the null and prove that the alternative hypothesis is the reality. We have covered a lot of ground today, so let us review the key takeaways. First, the null hypothesis is always our skeptical starting point, assuming no effect or no relationship exists. Second, the alternative hypothesis represents the actual theory we are trying to prove, claiming a meaningful difference truly exists in the population. Third, we must always assume the null is true until our data proves otherwise. By forcing ourselves to follow this backward-seeming process, we maintain strict scientific rigor. This ensures that our medical and biological discoveries are based on solid, undeniable evidence, rather than just random chance. You now have a strong foundation in biostatistical hypothesis testing.